letzter Mittwoch gefragt, was ist der Unterschied zwischen die zwei? So, die zwei sind nicht gleich. Okay? Aber die zwei Tabellen sind gleich, wenn wir diese Nicht-QT immer gleich wie PT. Es bedeutet, die QT ist immer gleich wie Nicht-PT. Es bedeutet, die zwei Tabellen, so hängt die Ausgaben hängen von den Eingaben ab. Aber wenn die P und Q immer nicht gleich sind auf jede Zeit, dann sind die zwei Tabellen gleich. Is this okay? Okay. Let's look at these two tables again. These two tables are naturally different. One has P, another has Q, when R, T, and ST are both 1. The others are the same except the last one, right? They are almost the same except the last row. But if we force ourselves not to make them different, what can we do? We make sure that the not QT is always equal to PT. That means that if one of them is 0, another is 1. As long as we can guarantee this all the time, then they are the same. Okay? Is that clear? Okay, so we get S. So, das haben wir schon früher gesagt. Das kann man so machen. So, das ist, wenn wir über die Q und P mit diesem Format gucken. So, hier, das ist P nach 2 Stufen. So, dann wenn dieser Obergatter schneller ist, dann es bedeutet dieser P plus 2 Delta, so das haben wir, ist eine Nentgatter. So das ist einfach die Negation von Art und dieser Eingaben Q von Typ T plus Delta. Okay? Dann wollen wir weiter, das ist einfach Negation von zwei Variablen. So, das ist die Negation von A und B ist gleich wie die Negation von A oder von B. Negation von B, das ist De Morgans Gesetz. Dann nennen wir hier einfach an. So, die Negation, so die nennt, geht A und Q T plus Delta ist gleich wie die Negation von A oder die Negation von Q plus T Delta. Und was ist Q plus Q von T plus Delta? Das nach einer Stufe. Das ist einfach die Negation von S und P plus Delta. So, das ist einfach die Ausgabe in letzter Stufe. Die Negation von Negation, dann es ist ohne Negation. Und dann können Sie Mathe machen. Am Ende ist einfach so. Okay? Das kann man auch mit anderer Fahrt, das Nengatter, unten ist schneller, dann bekommen wir diese. Okay, das ist einfach, wenn wir diese Tabelle nicht dort ausführen mussten, aber das kann man langsamer berechnen. So, was haben wir schon geguckt? So, fast oberes Nengatter schneller ist, dann der Wert von P in 2 Stufen am Ende ist die Negation von A oder S und nicht QT. Und im zweiten Fall, wenn das Nengatter schneller ist, dann ist P nach 2 am Ende ist die Negation von A oder S und PT. So, die zwei sind nicht gleich, wie ich schon früher gesagt habe. Aber fast, wenn wir P am Zeitpunkt T und die Q von Nicht-Zeit T immer nicht gleich sind, oder P am Zeitpunkt T gleich die Negation von Q von Zeit T ist, dann ist das Verhalten an unser P stabil. Okay, das ist für P und das kann man auch gleich gucken für Q, das ist auch gleich. Okay, so es bedeutet, wenn wir diese Latch benutzen möchten und abhängig von der Geschwindigkeit von und Gatter brauchen, dann müssen wir einfach die zwei P und Q immer nicht gleich sein. Immer nicht gleich garantieren. Okay? So, wir brauchen einfach diese Forderung. Diese Forderung scheint zum ersten unmachbar, weil es gibt diese Möglichkeit. So, wenn wir einfach A zum Nur und S zu Nur setzen, dann haben wir einfach Probleme, dass Q und P gleich sind. Was ist unsere Lösung? Ist einfach. Wir vermeiden solche Fahrt. Das ist nicht verfügbar. Diese Möglichkeit benutzen wir gar nicht. Okay? Das ist verbieten. Ein Verbot. Okay? Aber es scheint einfach aus. Wir sagen einfach, es gibt keine Möglichkeit, dass man A aus Nur und S aus Nur einsetzen. Aber wie geht es? Wenn wir von dieser Kombination Nur 1 und 1 Nur umsetzen, dann es gibt eine kleine Wahrscheinlichkeit dazwischen Nur. Das ist nicht gut. Und das zerstört unser Konzept. Es bedeutet, wenn wir solche Nur und Nur verbieten möchten, dann müssen wir die zwei Eingaben Art und S gleichzeitig messen. Es gibt keine Möglichkeit, dass wir einfach Freiheit geben, sodass man nur 1 und 1 nur wechselt, ohne kontrollieren. Wir müssen einfach kontrollieren. Okay? Das ist unsere Forderung. So, dann gucken wir jetzt. Es gibt keine Nur mehr. Und wenn wir einfach A aus Nur, S aus 1 setzen, dann setzen wir P zum 1. Das ist sogenannten Set. So, wir setzen das Speicher zu 1. Wenn A 1 ist und S nur ist, dann setzen wir P zu Nur. So, das ist einfach Reset. Und wenn die beiden 1 sind, dann lassen diese P unverändert. So, das ist kept. So, wir haben dann 3 Funktionen zu schon realisieren. So, Set nur 1, setzen wir einfach P zum 1. Und 1 nur, setzen wir einfach P zum Nur. So, das ist Reset. 1 lässt P unverändert. Das ist unchanged. Und es bedeutet, dieser bei stabilen realisieren wir schon ein Bit Speicher. Das können wir einfach das Speicher kontrollieren, um einzusetzen, um nur zurücksetzen oder weiter benutzen. Okay. Wenn wir Tick haben. Das haben wir jetzt das erste Fazit zum sequenzierten Schattungen. Wir brauchen diese Latch. Latch ist ein Kreiser in Schattennetze sinnvoll für Speicher. Es gibt neue Funktionalität. Bisher haben wir immer ohne Kreiser gemacht. Das ist unser erstmal eine Kreiser. Und die Analyse ist natürlich ein bisschen schwierig zu verstehen, aber einfach zu Hause noch einmal durchgehen, das ist nicht so schwierig zu strukturieren. So, wir brauchen ein bisschen strukturiert Entwurf, sodass wir mehr kompliziert Schattennetz entwürfen können. Das brauchen wir Automaten. So, was bedeutet hier? Wir brauchen ein Formos-Modell vom Automaten. So, Automaten kann man schon in unserer früher hier Getränke kaufen oder Snack kaufen. Das geht natürlich mit solchen Automaten und kann man auch mehrere Dinge zu steuern. So, was ist ein Automata? So, es gibt, wir können Automaten benutzen, sodass wir Eingaben zu verarbeiten. Automata erzeugt auch eine Ausgabe. Es ist immer in einem Zustand am jeden Takt. Als Arbeit eben nur immer in Takten und es ist ganz deterministisch. So, wenn wir gleich Inputs haben, Eingaben haben, produzieren wir immer gleich Ausgaben. So, was ist ein Automaton? Okay, sorry. I had to speed up a little bit because we have been too slow for some time. So, Automata. So, wir haben zum ersten Zustände, or states of English. So, Q ist die Zustandsmenge. Wir nennen an in dieser Vorlesung, dass Q ist endlich. Das bedeutet, die Anzahl von den Elementen von Q ist nicht unendlich. Okay, oder sogenannten endlich Automaten. Sagen wir, wenn wir solche Menge haben, dann brauchen wir auch einen initialen Zustand. Das ist Q nur. Aus Startzustand. Dann gehen wir zurück hier. Es gibt Eingaben und Ausgaben. So, Eingaben nennen wir mit Eingabesalphabet Sigma und Ausgabe ist Ausgabesalphabet Delta. Dieser Delta ist unrelevant von unser Delta von ein paar Minuten. Okay. So, dieser Delta für Automaten ist unrelevant für die Delta, wir vor ein paar Minuten vor Latch schon erklärt. Und dann haben wir die zwei Dinge. Dinge 1, zuerst ist diese Zustandsüberführungsfunktion. So, wir sind jetzt in einem Zustand. Okay? Wenn wir eine Eingabe bekommen, sollten wir zum anderen Zustand übergehen und wir definieren solche Überführung mit Funktion Delta. So Delta, kleine Delta, ist deswegen ein Cartesian-Produkt von Q, so Verhältniszustand, wir sind jetzt, und die Eingabenalphabet. So Q mal Sigma, so für jede Q, für jeden Zustand und jede Eingabe sollten wir zum anderen Zustand gehen oder gleich im gleichen Zustand bleiben. Okay? So, das ist eine Funktion mit zwei Eingaben, ein Element von Q und ein Element von Sigma. So, große Q ist unsere Zustandsmenge. Große Sigma ist unser Eingabealphabet. Und die zwei zusammen nennen wir als Eingaben. Und es ist eine Funktion mit den zwei Eingaben. Dann produzieren wir einen neuen Zustand. Und dieser neue Zustand ist unser Ziel. Wenn wir in diesem Eingabenzustand, in diesem Automaton ist und eine Eingabe von Sigma bekommen, dann gehen wir zu einem neuen Zustand. Okay? Bisher ist es alles in Ordnung oder nicht? Ich nenne noch einmal zurück. So, wir haben ein Automaton. Was ist ein Automaton? Es gibt Zustände, es gibt Eingaben, es gibt Ausgaben. Okay? So, Zustände, so wir nennen an, dass wir endlich Zustände haben. So, diese Menge, diese Elemente von Zuständen ist in Set-Menge Q. Okay, dann haben wir alle Zustände. Und dann haben wir ein paar Eingaben, Sigma. So, für jeden Zustand, so, das Automaton kann an jeder Zeit nur in einem Zustand bleiben. Ja? Deswegen müssen wir jetzt, wenn wir eine Eingabe bekommen, von Zustand zum Beispiel kleine Q, dann Eingaben 1, dann führen wir entweder zu einem neuen Zustand oder bleiben wir im gleichen Zustand. So, deswegen brauchen wir diese Überführungsfunktion. Das ist mit Sigma, das ist mit Delta definiert. So, bis hier alles in Ordnung oder nicht? So, wir haben von hier bis hier schon diskutiert. Any question about loss?
So basically, if I understood it correctly, kartesisches Produkt von Q and so basically it's like here combination of the state and
so let's say I have 10 states. I have 2 inputs. So if you are in state, you have 10 states encoded from 0 to 9. 2 inputs encoded as A and B. If I'm in state 0, I receive A, I have to go to state 9. Okay, I have to define the transition of the automata according to the current state and the input it receives. How do I move to the next one? Think about how you design automata. It's always like that. Yeah.
So it kind of depends on the input and
No,
the
no,
previous...
you have to define everything starting from the states you have. If you are in state X, you receive input A, where do you go? You have to define that. And you have to define that completely.
So I either go to the next state or just...
You can stay, you can stay in the same state, or you have to change to a new state. state transition has to be defined based on the current state of your system, the automata, and the input you receive. And you define it with this small delta function.
Ah, so it's like, okay, it's function, okay.
Okay, good. So now, gut, so far so good. Wir in dieser Vorlesung diskutieren zwei verschiedene Automaten. Das erste ist sogenannte Mini-Automata. Im Mini-Automaten die Ausgabe, so wir haben auch dort gesagt, dass Automaten auch erzeugen Ausgabe. Im Mini-Automata, diese Ausgabe ist mit gleichen Dingen wie Zustandsüberführungsfunktion definiert. So, wir definieren die zwei, Delta und Lambda. Delta ist die Zustandsüberführungsfunktion mit Cartesian-Produkt Q mal Sigma für die neue Zustand. Und wir haben auch diese Ausgabefunktion. Dann produzieren wir gleichzeitig auch die Ausgabe. Okay? Aber es gibt kein gleichzeitig. Wir müssen auch diese Ausführung machen. Das bedeutet, wenn wir von einem Zustand kleiner q und eine Eingabesymbol W bekommen, dann müssen wir in neuen Zustand wechseln und auch eine Ausgabe produzieren. Okay? Machen wir zuerst die Ausgabe und dann wechseln wir der Automata in den neuen Zustand. Okay. So, Daniel, please help me make a note. Kleine Delta. So, yeah. Any question? No, einmal. Maybe you keep this time.
Doesn't it make more sense that it will firstly change the state and then give the output?
Yes, I have always asked myself the question. Let's think when you change to a new state, that you may think that this is already done in a transition and you receive a new input. You screw it up. So it's better to write output and then change to a new state.
Okay.
Of course, you can say that it happened at the same time, but you need to define a sequence. We cannot, your brain doesn't work with this at the same time, but you can logically think that it happened at the same time.
Because the difference in time is very small.
Yes. Yeah. But let's say we do this way. So we first write, produce the output, and then change. It doesn't. If you change first and you forget to write the output, you lose a lot of points in the exam as well.
Okay.
Okay. Good. Ja. Was ist unser nächster Folien? Keine Ahnung. Okay, ein Beispiel. Okay, so. Hier ist ein Beispiel. Wir haben drei Zustände, Q0, Q1 und Q2. Zwei Eingabenalphabeten, 0 und 1. Dann produzieren wir ein paar Dinge. Ja? Okay, so was können wir dort machen? So, wir haben Zustände Q0, Q1 und Q2. Dann es gibt Eingabe Q0, wenn wir nur bekommen. So, gehen wir zum Q1 und produzieren wir A. So, wir schreiben in unser Zustand. Es gibt zwei Funktionen für diese Überführung. So, wenn wir nur bekommen und dann produzieren wir A. Okay, das ist auch gleich. Q nur bekommen wir 1, dann produzieren wir C. Und dann Q1, wenn wir nur bekommen, so Q1 nur zum Q nur, so 1 und produzieren wir C. Q1 zu 1, oh, Entschuldigung, so das ist nur. Und dann das ist 1 zum Q2 und dann produzieren wir B. Q2 nur geht zu Q1. Produzieren wir A, Q2 geht zu Q nur, dann produzieren wir B. Okay? Gibt es Fragen? So, es scheint so aus. Und dann können wir einfach weitergehen. So, wir benutzen auch mit zwei Zyklen, zwei Kreise für den Startzustand. Das bedeutet, wir fangen mit Q nur an. So, dann, wenn wir hier in Q nur haben, dann bekommen wir nur. Das bedeutet, wir gehen zu Q1, wir produzieren zum SA und dann wechseln wir zum Q1. Ja? Dann jetzt der Automata ist im Zustand Q1, dann bekommen wir was als 1, dann produzieren wir B und gehen wir zum Q2. Dann nur gehen wir zum Q1, produzieren wir A, produzieren zum SA und dann geht zu Q1 und weiter. Okay? Gibt es Fragen über Mini-Automata? So it's a very simple game. Okay, so just follow the game. Of course, you have to design your own game. I like the old days, we use the Klingons cannons, but seems that no one knows Klingon anymore. Does anyone here speak Klingon? Do you know what Klingon is? No? See, this is a difference of generations. Star Wars? Yes. Okay, then at least those who watched Star Wars before, you probably know Klingons. I'm sorry, Star Trek. Sorry. Star Trek, you will know Klingons. If you know Klingons, you know their cannons, and then you can design automata for their cannons as well, okay? But we don't have this anymore, right, Daniel? How is our automata exercise?
I think that's something boring.
Something, okay. I like the Klingons exercise more, but seems that even the assistants don't like them anymore. So you will have to design your automata. Not this one, this is too easy. Okay. That's why you usually say the professor teaches only the easy stuff, the exercise is more difficult. The good thing here in our lecture is that the exam is not more difficult than the exercises. So if you are able to master the exercise, you are able to master the exams as well. Okay. Okay, so dann, natürlich, wir können auch nachfragen, gibt es Möglichkeiten, dass wir mehrere Mini-Automata konstruieren können, sodass die Automaten mit gleichem Verhalten. Das geht natürlich. Ja? So, es bedeutet, jetzt können wir sagen, zwei Mini-Automaten sind äquivalent, wenn vor jeder Eingabe die gleiche Ausgabe erzeugen. Das bedeutet, Sie haben zwei Mini-Automaten definieren, aber die zwei hatten gleiches Verhalten. So das die zwei sind äquivalent. Natürlich, unser Wunsch ist, dass wir nur die kleinen Automaten produzieren. Hier sehen wir nicht so ernst, aber es gibt auch mehr Dinge, die später in theoretische Informatik Vorlesung oder Logik Vorlesung, Sie können mehr dort studieren. Okay, so ich habe schon gesagt, wir haben zwei Modelle in unserer Vorlesung. Das erste Modell ist Mini-Automaten. Was ist der zweite? Ist More-Automaten. Okay, was ist der Unterschied zwischen die zwei? Okay, gucken wir zum ersten. Es gibt auch Zustandsmenge. Es gibt auch Startzustand. Es gibt auch Eingaben ins Alphabet. Es gibt auch Ausgaben ins Alphabet. Es gibt auch Überführungsfunktionen. Die alle sind gleich. Von hier bis hier sind gleich wie Mini-Automaten. Okay? Das bedeutet, der letzte ist nicht gleich. Ja? Ansonsten haben wir gleich Automaten definiert. Was ist der Unterschied? Gucken wir noch einmal. Das ist more automaton. Take a picture on your plan. Let's go back to mini automaton. Take a picture here. So this is a Cartesian product of Q and sigma. More automaton. Einfach Q. Haha. Okay. So now, what does that mean? In a mini automaton, we describe what to produce at the edge of the transition. In a more automata, we describe how to the output in our destination in the node. So jeder Zustand hat nicht nur die Name von dem Zustand, die Ausgabe der Zustand produzieren mussten, wenn jemand von anderem Zustand in dieser Zustand wechselt. Okay, so repeat that again. What does that mean? Your output function is defined at your state. What does that mean? When you enter this state, you produce one output. So that means that if I move from state A to state B, I produce one output of state B. If I further move to state F, I produce an output of state F. I further move to state Z, I produce the output of state Z. If I further move to state S, I produce the output of state S. I don't care where you come from, I just produce the output at the destination. Seems that we are losing our signals from time to time. Okay? Any question? So the new Zustand, not the old Zustand. So what do? We so we are at a status of Zustand Q, and we have an input W, so it's the same as mini automaton. Okay, so we again first write the output. Where can we see the output? We know that we are going to move to the destination. This destination is described as node delta of Q, W. So we just produce that. And then we change to the new state. It's the same as before, but we don't label the output at the edge. Instead, we label the output in the destination node. Okay? So der Unterschied zwischen More-Automatan und Mini-Automatan ist nur hier. Und natürlich auch hier. Any question? No? Das hier wird fester. Okay, gut. Sorry? Which one is better? This is the question I like the most. Whenever we introduce two models, we ask ourselves, why does he have to talk about two models? Which one is better? Or which one is easier to understand? Or are they the same or are they different? Let's start from the case. Are they the same or are they different? They're different, huh? First, they are different. But do they have the same power or not? Okay, what do I mean by that? We talked about equivalence earlier, right? So two mini-automatas are considered equivalent if for every input they produce the same output. Okay, so we ask the same question. Is it possible that there's a problem or there's a case we can only use more automata, but we cannot use mini-automata? Or we can only use mini-automata, but not more automata? Or they are different in a way that they are problems that can be only described by more automata, but not mini-automata? And there are problems that can only be described by mini-automata, but not more automata. So let me repeat the question again. If we want to compare two models, first we want to see whether one is better than another, or they are incomparable. So if one is better than another, that means that then there must be a problem that can only be modeled by one of them, but not another of them. They cannot be equivalent, okay? Or if they are incomparable, that means that there must be a problem that you cannot describe with one of the other, and there's yet another problem that you cannot describe with another as well. So that means that there's a problem that cannot be described by mini-automata, but can be described by more automata, and there's yet another problem that can be described by more automata, but not mini-automata. Okay, so since we talk about these two, right? So, I mean, it looks like that more automata is weaker, right? It looks like. Yes?
It seems like they are the same.
It seems that they are the same.
Ja, ein Mini-Automat, man hat halt Ausgabe, Eingabe, das Ganze hat man auch bei Mini-Automat, also die sind gleich.
Die sind gleich.
Wie ich das hier sehe, das hat man auch bei Mini-Automat.
So, Mini-Automata.
Eingabe, Ausgabe und dann Eingabefunktion, Ausgabefunktion. Startzustand hat man auch und Zustandswechsel.
So, es bedeutet, wir sollten überweisen, dass für jede Mini-Automata gibt es eine äquivalente More-Automata und für jede More-Automata gibt es ein äquivalent Mini-Automata. Okay? So machen wir so. Okay, they are the same. They are the same power. We talk about these two because we want to do this for the first case that you show that they are the same. But it's easier to describe your problem with sometimes with more automata, sometimes with mini automata. You make your own choice. Or the examination forces you to choose one of them and don't mess it up. Okay? If the question is a mini automata, don't answer more automata. If a question is more automata, don't answer mini automata. Okay, good. So, The first one is easier. So two more automata are, so with the third automata is this mini automata equivalent. Was bedeutet jetzt, wir setzen einfach unser, so wir haben more automata, ja, lassen wir einfach die Ausgabe von Zustande zum Überführung. Das geht einfach. So, fertig. So let's say, usually, if you look at the case, it's easier to use mini automata because of this. You don't need more automata. Okay, so this is easier to understand. What you do is that every node has an output, right? In more automata, let's took the output to the Überführungsfunktion. Okay, so to the edge, and it's done. We don't have to do anything else. Any question for this? The next one is more complicated. Okay, so next one. So for every mini automata, we can also have an equivalent more automata. How does this actually work? It's a bit more complicated by that. So let's look at one example first. So let's assume that we have a mini automata like this. It has 3 states, 0, 1, and question mark. What this automata does is that if you have consecutive zeros, it will always produce 0. When you switch from 0 to 1, the first time it will still produce 0. The second time it will start to produce 1. So you allow to have this data filtering. Is that filtering or not? Great term. What is? And this field, you basically filter the isolate bits from that string. So you have 0, 0, 0, 1, 0, 0, 0, that 1 would become 0. If you have 0, 0, 1, 1, 1, 1, the first one would be 0, the rest would be 1. Okay, so that's how the automata does. Okay, and then you just do it in the way that you produce, you say you have 3 states, 0, 1, and an uncertain state. Let's call it question mark. If you're in state 0 and you receive 0, you keep yourself in state 0, produce a 0. If you are in state 0, receive 1, you go to the question mark state, and at the moment you still produce 0. If you are in the state 1, you receive 1, you produce 1, stay in state 1. If you're in state 1, you receive 0, you produce 1, and transit to the question mark. If you're in the question mark and you receive 0, you go to the 0 state, produce 0, and go to the 0 state. If you're in the question mark state, you receive 1, you produce 1, and go to the 1 state. That's it. That's the automata. Any question of this automata?
So basically with this Mealy automate, we are trying to represent Muri automate.
No, this is still mini automata. This is still mini automata. I'm just explaining this automata. And first explain what this automata does. It filters the isolated bits. So if you have multiple zeros and only 1 in between, this 1 would be replaced with 0. If the multiple 1s and 1 0 in between, this 0 will be replaced with 1. You only change your state to 1 if you have consecutive 1s. Only change your state to 0 if you have consecutive zeros. Okay? That's the automata. or the automata does. Okay? Yes. Can you pass to the back?
Wenn ich das richtig verstanden habe, ist der Doppelkringel da der Startzustand und gleichzeitig der Endzustand oder
Der
wie
Startzustand ist Zustand nur. Wenn wir zwei Kreise haben,
Ja.
der Zustand ist unser Startzustand.
Und was ist denn der Endzustand? Der Endzustand.
Es gibt keinen Endzustand.
Ach so.
Es ist ein Spiel.
Okay.
Wir öffnen jederzeit einen Zustand für diese Automata und wir bleiben hier, bis wir nächste Eingaben bekommen. Ja.
Okay.
Ist das klar?
Okay.
Of course, you can define Endzustand if you want to terminate, but this is not what we do.
Also bei Milli-Automaten hat man dann keinen Endzustand.
Es gibt keinen Endzustand
Okay, ja.
in Automaten.
Und bei Mori?
Bei
Bei
Mo
Mo
auch nicht.
auch nicht.
Alle nicht.
Weil
You can define an Endzustand by saying that I turn off the system if you reach that state. Yeah, that state is the end of the system, but you have to define that, and it's outside the automaton definition. Okay? Any question for this mini automata? The reason why this is mini automata is because we have the input and the output defined at the edge. Oh, sorry, at the transitions. You don't know the definition of edge yet. Yes. Can I get a microphone? Yes. This is.
So why we don't have a value where the question mark is?
The value?
Yes.
You mean the value of what?
Da wo das Fragezeichen ist.
This is only a name. 0,
Okay.
1, and question mark are just names. I can also define them as X, Y, and Z.
Okay. Thank you.
These are just names for fun, okay? You can define them as big, small, medium, anything you want. Okay, so more automaton. What do we need to do to make this a more automaton? We want to prove their equation, right? So that means that for this mini automata, we are supposed to be able to convert this to a more automaton. How should we do that? We cannot label the output in the transition anymore. So we have to label the output in the node. So let's first look at this. We have 3 states. We have 2 outputs. The output values are either 0 or 1. So that means that let's just put all possibilities there. Okay, so I'm going to write down. So I have state 0, 0, 0, 1, question mark 0, and question mark 1, and then 1, 0, and then 1, 1. So with this one, what I'm labeling here is that for the first data in each state, the first one represents the original label in the state, as you said. If I want to call it big, then I call it big. And the second one is the output when this state is entered. Okay? Good? So with this idea, now we know that when you enter this state, you will never produce 1. So this 1 is meaningless. Or let's just keep it first before we delete that. Okay, so then we will start from, 0, 1. So this, I think we should still delete this one. It's going to destroy our stuff. By looking at this one, you will never produce 1 when you are in this 0 state. So we can take this out, and we will never produce 0 when we are in this state. So we take this out. So technically, we have only 4 states, right? So now we can do the transition. So the first one, this is our initial state. Okay, if we receive 0, So if we receive 0, we stay here. If we receive 1, we go here. And also similarly, if we receive 0, we go here. If we receive 1, we go here. If we are here at this state and we receive 0, we go back here. If we receive 1, we go here. If we receive 1 here, we go here. If we receive 0, we go here. Oh, I'm sorry. I'm so sorry for this. So if we receive 1, we go here. Okay. If we receive 0, we are in Zustand. If we receive 1, we go here. If we receive 0, we go here. Sorry. You don't switch between the question mark states. Yeah. Any question for this? Hope I did not make a mistake. Wait a second. So many hands. Did I make any mistake? Yes.
Beim Zustand Fragezeichen 0, da kommen wir nur mit der 1 woanders hin. Und was mit der 0?
Nein, wenn wir in Zustand nur, so wir gehen von nur zum Fragezeichen nur. Ja?
Ja.
Dann, wenn wir noch eine nur, wenn nur eine, wir bekommen ein 1, dann wechseln wir zum Fragezeichen nur.
Ja, und dann, wenn wir eine 0 kriegen, wohin dann?
Dann gehen wir zu nur.
Ach ja, okay,
Ja.
habe ich übersehen.
Ja, gut. Es gibt noch eine. Okay, gut. So, let me check whether I made a mistake. I don't think so. Yeah. Okay, so what did I do? Symbolically. So, of course, remember that we also had these 2 that I just removed. So we had this 0, 1, and 1, 0 that we just did, right? But they had nothing. You cannot reach these 2 states. Any of these 2 is not reachable. So they are removed anyway. But if we really do this systematically, what we first do is that we create new states. What are the new states? The new states are the Cartesian products of the original states and the output that we have. And we basically now say that if you are in this state and you somehow switch in, then you get that specific output produced. So for every state, there must be an output assigned to it. So let's just enumerate all of them and become new states. Okay? That's the first one. Now, what did I do next? Next, originally, you switch from, you move from this state 0 to, with this one, output of 0. That means that if we want to produce this one, we are going to switch to the question state that has a specific output of 0, label there. And we are going to say, if I receive 1, I'm going to switch there. Okay? So I just look at the original mini automata. And for every state and every output I produced, I'm going to check which input it's needed to switch there. And I specify all of them. Okay? And by doing so, we create more automata, and that has the same behavior as the original mini automata. And so, what do we have? Q stick is die Cartesian Produkt von Q und Alphabeten und natürlich zusammen mit empty, wenn wir diese Möglichkeit, keine Ausgabe produzieren, für diese Überführung gibt. Und diese Q nur setzen wir zum S zum Q nur und Y nur, keine, wenn es gibt. Und QV ist ein Zustand in unserer Menge von Q-Stick. Dann spazieren wir das Übertrag, so, wenn wir in Mini-Automata von Q-Stick zum Eingaben W, dann setzen wir einfach diese gleiche Überführungszahl, aber dann setzen wir diese mit Ausgaben V. Okay, das ist gleich für unsere Überführung und Ausgabefunktion. Okay, es bedeutet, für jede Mini-Automaton können wir einfach auch ein äquivalentes More-Automaton produzieren. Ja? Das ist einfach dieser Fazit. So, hier ist der Mini-Automat und wir haben auch ein Äquivalent More-Automaton entwickelt. Any question? So, why do we need to do automata? I hope it's now clear. No, not yet. So why do we need to do automata? Because it has this concept of ticks. In every tick, we produce the output, and then we change to a new state. The tick of a layer is basically relevant to the way how we control our flip-flops or latches. So, now coming back to our latch. We had the latch defined earlier, and if we want to control it by what I said earlier, that we can set R and S, but we must set them at the same time. Then the configuration of R and S will become our input. The state of this automata can be used to describe the data that we store as 1 bit in that latch. And if we can control how we change the state of the system, then we can decide what the current state of the latch is. So, as I said, we have 2 states describing what is stored in a memory in this latch. Let's assume that we start from 0. We can control this with these 3 possibilities, 0, 1, 1, 0, and 1, 1 for R and S. And the output is the output of the memory. Okay. So what we can do is that we can write down the memory. So if we are in state 0, we receive 0, 1. And let's look at the output of P over here. So when we receive 0, 1, the output will be 1. When we receive 1, 0, the output would be 0, and the memory goes to 0. So it goes here. And let me do it again. Sorry. So let me do it again. Okay. So we have the memory state 0 and 1. So that means that at the previous time t, that P was 0 and 1. Now we receive 0, 1, or 1, 1, 0, or 1, 1. Okay, so if we were in 0, and we receive 0, 1, we will move to 1, right? This moves to 1. If we receive 1, 0, we will stay at 0. If we receive 1, 1, the value of p doesn't change, so we stay at 1. So I go back to the other side. If we are in state 1, we receive 0, 1, and we stay as it is. If we receive 1, 0, we will switch to 0. And if we receive 1, 1, we will state as this current state. Okay, now the output basically describes which value it goes to, the memory that you actually use to describe that. Okay? So, but if you do so, it doesn't work because you don't have a tick signal. You need to tick that. How do we tick that? The latch we described earlier has no tick. We don't know when we can change R and S. It's possible that R and S are changed at the same time to 0, 0, which we don't allow that. So what can we do? We add one additional signal. The signal is called T. And there are 3 ways to do the signal. We are not going to talk about that here. I'm going to talk about that right before Christmas. There are 3 possible ways. One is called I forget the first one. So one is called, there are 2 ways. One is called something I will figure out at some point. And the next one is called edge trigger. And the edge trigger can be triggered in a positive way or the negative way. So what is Pekio-Steuerung in English? It's called edge triggered. What is the other one? So basically, the first one is like when you are switch from 0 to 1, when you are stable at 1, it triggers. Level trigger. Level triggered. One is level trigger, another is edge trigger. For the edge trigger, it can be positive trigger or negative trigger. So basically, one of these 3. We don't care about them. Let's say you take one of them. So this is not the details we want to discuss over here. So we now see it's like, so we have this additional part. Now we link R and S in addition to the tick signal, the clock signal. The clock signal, when the clock signal is triggered to 1, then you are allowed to change the values of R and S. And because you link these 2 together with the synchronous clock signal, you change these 2 signals always at the same time. Okay? So with this one, originally, this is because of T. So when we trigger, T is 1. So this becomes negation of R. This is negation of S. So basically, originally we said that, RT and ST. Originally we said that we don't allow 0, 0. Now we don't allow 1, 1 because of this negation. Okay? So originally, in all my explanations, I look at the P, but now I'm just going to look at the Q. So it would be still the same, just because I flip everything around. Okay, so if R and S are both 0, then the flip-flop remains as Q. If R is 0, S is 1, the flip-flop is 1. If R is 1 and S is 0, we set it to 0. So in that case, again, R is for reset, S is for set. If one of them is 1, then you prefer that one. So if R is 1, S is 0, you reset. So the Q becomes 0. If S is 1, R is 0, you set to 1. If both of them are 0, you keep as it is. The flip-flop is keep as it is. So Now it's time to talk about the name. The latch with 2 states did not have the clock signal. That is called latch. The flip-flop has the context signal, and therefore you can use automata to model the behavior of R and S control. The reason why it's called flip-flop is that if you flip one of them, the other one flops. So it's never the same. You have 2 bits, and they are always different at any point in time. So therefore, it's called flip-flop. You cannot make them the same. The reason why you don't make them the same is that you don't want to be dependent on the speed of your gates. The example we use here is the NAND flip-flop. You can also use NOR flip-flop. So basically replace them with NOR. And this is therefore called RS flip-flop. Reset, set, flip-flop. Any question for the flip-flop? First one. If not, let's do the next one. It's called D flip-flop. So D flip-flop is an extension of RS flip-flop by putting a negation over here. So basically, it allows you to only have 2 different values of R and S. So you would, so let's have a look. So that means that if D is 1, if D is 0, if D is 0, then this is 1 and this is 0. So this is reset. Okay, if D is 0, then Q is also 0. If D is 1, if D is 1, then this is 0, and this is 1, then it's set. Oh, so surprisingly, only with this possibility. So when D is 0, the flip-flop is set to 0. When D is 1, the flip-flop is set to 1. Well, what does this have to do with us? Well, it's basically reset and set. We have to keep in mind that everything is ticked. That means that it's delayed by 1 tick. So if you use such a flip-flop, your flip-flop has the possibility to delay the behavior by 1 tick with the clock signal. So it's called delay flip-flop. When we look at the RS flip-flop, we may have we may ask ourselves, well, we look at the 3 steps: reset, set, and keep the same value. Is it possible that we take a negation of the current status or not? So RS flip-flops allow us to do reset, set, and remain the same value, keep the flip-flop as it is, but we may want to do the negation. Okay? Let's create a new flip-flop for that. Then we have all possibilities. So I will basically reset to 0, set to 1, keep as it is, and take a negation of it. What else can you do to control 1 bit? You cannot do anything more, right? Then, if we can allow the possibility to take a negation, then we basically have the complete function to control 1 bit. Okay, so let's have a look of this idea of JK flip-flop. The JK flip-flop works as follows. It takes a jump signal and a key signal. The key signal is therefore connected to R. The jump signal is connected to set. So if here is 1, then you plan to kill it, right? If jump is 1, then you plan to jump to 1, right? So jump is basically the replacement of set, and kill is the replacement of reset. So basically, what we want to do is to make the possibility that we are able to replace that. So when we connect this is that JK 0, 0, and RS will be 0, 0. Then we basically would take this as it is, Q. If Q is 1, then we plan to set it, if Q is 1, jump is 0, then we plan to set it to 0. So we need to do is to connect this to the case that S is 0. And then in this case, if I is 1, so if I is 1, then it will set to 0. If I is 0, it will be kept as it is, so it stays as 0. Okay? Good? That's a trick. Let me repeat this again. We plan to kill this flip-flop by setting it to 0. So let's set jump is 0, kill is 1. If you look at this circuit, it goes to R is set to Q, and S is set to 0. So if Q is 0, then this is 0, 0, then this remains as 0. If Q is 1, then R is 1, S is 0, then this is reset to 0. Okay, so this is the same. So we check this, and this is the same over here. Okay, the only thing that's slightly different is that J is 1 and K is 1. So jump is 1 and K is 1. We don't know whether we are jumping or we are killing, right? So for this case, for 0, 0, we keep as it is. For 1, 1, we take a negation. How do we make sure it's a negation? Let's just check the truth table. So R in this case is Q, as in this case is the flip-flop, the flop part, right? Not Q. So basically, so if I is 0, S is 1, 0, 1, then Q is 1. If I is 1, S is 0, then Q is 0. So basically, we reach this negation of Q. So JK flip-flop allows us to have the 4 possible states over here. We can also take this T flip-flop. T flip-flop is basically the status. If T is 1, you tackle it. You take a negation of Q. If T is 0, then you keep it as it is. So T flip-flop basically can be implemented by JK flip-flop by making sure that if T is 0, you go here, and if T is 1, you go here as well. So the T flip-flop over here. Okay. So we have talked about 4 flip-flops. Sorry, 4 types of flip-flops. So RS flip-flops, T flip-flops, JK flip-flops, and T flip-flops. So why do we need to talk about that? We want to use the flip-flops to control a memory such that we can use the automata to control what we do with the memory. Okay. So for us, what's important here is not the values of those flip-flops. What's important for us is what we actually get after putting the control signal in. So let's assume that we have the Zustandstabelle. Then we want to change that to look at the control table. What is the control table? We have the current state and the state that we need to go to. Therefore, we need to consider how we design our signals of J or K or R or S or D or T to make sure that we are able to control the flip-flops correctly to implement the computation using memory. Is that clear to everyone? So we have talked about the memory so far, right? So we look at the RS flip-flops. We look at JK flip-flops. We look at D flip-flops and T flip-flops. So the key important thing is that if we want to implement 0 plus 0, and then we want to use a carry bit as our state, then what's important for us is to control how we start the information to that single bit in our flip-flop. So what we need to do is to build the control table of our flip-flops. Can you pass to me?
So basically this new table is a replacement for that Zustand-Tabelle.
Let's look at the next one. So what do we need in this table? So we have the all Zustand. So we are looking at 1 bit. So far we only have 1 bit. We're going to stay with this 1 bit for a while. So if we have a D flip-flop, we have this status table. But for us, what's important is to control that control signal. So we are going to move from an old state to a new state. If we want to change from the old state 0 to a new state 1, we need to know which control signal we put to the flip-flop. So if it's 0, 0, and if it's 0 and ended up with 0, we should put 0. If it's 0 and end up with 1, then we should put 1. If it's 1 and we want to change that to 0, we should set D to 0. If it's 1 and the new one is 1, we should put D to 1. For D flip-flops, basically you are setting it. So it's only delayed by 1 tick. You can ignore the old state. But if you look at T flip-flop, it will be different. If you are originally 0 and you want to move to 0, you set T to 0. The original 0, you want to move to 1, you set T to 1. You are originally 1, you want to go to state 0, you set T to 1. On the original 1, you go to state as 1, then you go set T to 0. So if you are moving you are controlling a T flip-flop, then you need to take a look of the all status. If you look at the RS flip-flop, then you are moving from 0 to 0, then you have 2 ways. One is that you keep yourself as it is, as it was. So it's originally 0, so you can keep it as it is, put RS to 0, 0. Or you can put R to 1 and S to 0. So, but that means that R can be 0 or 1, so you have the freedom of taking any of them. If you are originally 0 and you want to change to 1, and you have flip-flop, RS flip-flop, then you have to set it. So it's R is 0, S is 1. Originally, you are 1 and you want to move to 0, you have to reset it. R is 1 and S is 0. If you keep as it is for state 1, then R is put to 0, S can be 0 or 1. You get a freedom for some options. Let's look at the JK flip-flop, which is more interesting. For JK flip-flop, if you keep the same, you can kill it, or you can just keep it. Okay? If both are 0, moving from 0 to 0. If both you move from 1 to 1, you can jump to 1, or you keep as it is. Okay? Now, if you are originally 0 and you want to go to 1, you can either jump or you can take the negation. So jump is arbitrary, but kill must be 0. from 0 to 1. So 0 to 1, jump is 1, but key can be arbitrary. It's the same if you want to go from 1 to 0, you can take a negation, or you can take a key, depending on which one is better. So the good thing of JK flip-flop is that you can take the freedom of this. Okay, I think I can finish that. So, why do we need that one? Let's finish this one. I need roughly 10 more minutes to finish this one. Am I too ambitious or not? So, what we want to do is that we want to design an n-bit adder. You learned how to do this earlier using the carry look ahead method, in 5 weeks ago we talked about that. Or you can do this repo at adder. So now we want to have a creative way of doing that. We only use 1 bit memory. And that nice bit of memory stores our carry bit. So I'm going to add from the last position, and then the status of the carry bit will be our status. It produces the sum bit. Every time when I add 2 bits, the sum bit is produced. The carry bit is my state that I'm going to use for adding with the other 2 bits in the next round. Okay, so let's see how this works. So we have the 2 bits that we get to add together with the state, the carry bit. The carry bit is either 0 or 1. We have 4 inputs, 0, 0, 0, 1, 1, 0, 1, 1. Basically, the 2 bits that we are going to add together with the carry bit. Okay, so now the output is our sum bit. The sum of the sum bit of the addition of the 3 bits. The 2 bits from the inputs and the 1 bit in the memory that we store as a carry bit. So if you are in 0, state 0, you receive 0, 1, and you produce 1. If you receive 1, 0, you produce 1. If you receive 0, 0, you produce 0, and your carry bit remains as 0. If you are in state 0, you receive 1, 1. Your carry bit would be set to 1, and you produce 0 over here. If you are in state 1, you receive 0, 0. You will produce 0, stay as it is. If you receive 0, 1, your carry bit goes to 1, and you produce 0. If you receive 1, 0, you produce the sum bit 0. The carry bit is set to 1. Yes, the same. If you receive 1, 1, you produce 1. Your carry bit remains as 1. Okay, good. If you receive 0, 0, it goes back to 0. So this is our automata. Right? So now what we need to do is to put everything together. So how should we do it? So let's do the second step. We have the input of 0, 0, 0, 1, 1, 0, 1, 1. We have the codilon of our output is 0 and 1. The codilon of our Q is 0, 1. So basically straightforward. So now let's look at what we have in our automata, in our Werttabella. So we have this is our old Zustand of carry bit, and this is our new Zustand of our carry bit. So we want to use JK flip-flops. The reason you can also do that with flip-flops, any flip-flops you want, but JK has the most freedom. So let's use the JK flip-flops. So I have state 0 going to 0, state 1 going to 0, state 0 going to 1, state 1 going to 1, right? What I need to do is to just write down the table. So let's look at these two and look at the reference of this one. By the way, you don't have to memorize. Do they have to memorize the table or not? I think we promised in the past that this is not relevant. Okay. I mean, you anyway will get a hint. The purpose is not to create this one. The purpose is to understand that one. Depending on which assignment you get, if your assignment is to design this circuit, you will be supported with this. If your assignment is to derive this table, then of course you will not get a hint over there. Okay, so now let's just do it over here. So 0, 0 goes to 0 star. So we basically put this table back to this table. So far so good? I mean, just look at the C. This is basically our cool art. This is our cool noise. Okay? Just map them back. So then you get all of them, and let's look at this, designing a circuit. So let's just do this. This is incomplete functions, but we have a lot of choices. Let's just go through all of them. So that means that for this, we can build the K-file diagram. So let me just draw it. So that means that this is 0, 0, 0, 1. Am I getting to the right position? I'm taking the wrong position. So 0, 0, 0, 1, star, 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 star. Okay? So you get this one, and then you get these two rectangulars, and you know that J is xy. Similarly, you do this for K. You know that K is not x and not y. Okay, so far so good. So it looks like this. And then the sum bit is basically the exclusive OR, right? We learned this earlier already. So finally, we produce this circuit. The circuit says that we do this x and y, and then J is basically xy, and K is not x, not xy, and C, the sum bit is the exclusive of these three. Okay, so we are done with this. But we need to have a circle, right? Everything is relevant to the memory. Where is our Q? So this is a JK flip-flop that we have here, right? So there's a Q and not Q. Okay, so where is our Q, by the way? We are almost there. Yes, please. Say up is our Q. So that means that we are missing this final circle. Okay, let me do it again. So what do we assume? We assume that we are looking at one bit for a carry bit. The carry bit is stored in our formula as C out. Okay, the old carry bit. That means that, and we are going to use this bit again and again, right? So let C out doesn't exist as an input. Let C out is in our 1-bit memory. And where do we store that in our 1-bit memory? It's stored in the Q value in our flip-flop. So therefore, this Q it goes back to the CR. With that, we created our circuit. And how does this circuit work? Let's have a look at one example, and then we are done with this. So let's start with the initial Zustand that our flip-flop stores 0. So 0 plus 1 plus 1. So what you will get is that 1 plus 1 stay with 0, and it goes in, and then your carry bit is set to 1, and you produce it 0. Okay? Then we receive an input of 1, 0. X is 1, Y is 0, and it goes like this. And then you go through the circuit. J is 0, T is 0, J is 0, K is 0. So it's J is 0 and K is 0. So your memory is kept as 1. But your sum bit is produced as 0. In the next case, you receive 0, 1. And then it goes in again as 0, 0 over here. So your sum bit is again kept. Sorry, your carry bit is again kept. You produce 0. And then next one, you will receive 0, 0. And then your JK flop has J equals to 0, K equals to 1, 0, 1. You are going to kill the flip-flop to 0. And then with this one, you produce 1, and your flip-flop is set to 0. Okay, and you go ahead. Now you receive 1, 1. Your JK flip-flop receives 1, 0. So it's jumped to 1. And you get an output of 0 over here, and so on and so forth. Okay, so with this, in every iteration, you move on to produce the carry bit for the next position, and then you take the 2 new bits in the next position, and then add the 2 new bits together with the carry bit, and then you produce the output accordingly. So this is very, very cheap, right? Because you only need 1 bit memory to do that. In fact, that JK flip-flop has 1 signal T and then a few NAND gates. This is super, super cheap, but it's just super slow. Okay? So any question about this? I'm sorry that I have to talk at the end in English, and then because I think if we do not do that, we are not able to reach this status. Next on Wednesday, I'm going to shortly explain this again. So the key idea is that you do 1 carry bit as your memory. You always keep the memory in mind, and when you receive 2 additional bits, you add them up. What you need to do is to decide how you control the memory, depending on your original memory status and the 2 additional bits you receive. And this is what we have done today. See you on Wednesday.